Good morning and welcome to Promess Incorporated. My name is Glenn Nausley. I'm an applications engineer. I've been here for 11 years now. I've been in applications specifically for 5.
Hi, my name is Scott Laske. I'm also an application engineer here at Promess Incorporated. I've been with Promess for roughly 16 years now. I started in our manufacturing department, and I've been with the application engineering group for about the last 10 years now. Today, we're going to be talking about using measuring probes to improve your assembly processes. Just in general, what a probe is, the benefits of using a probe, and why you might want to consider them for some of your assembly processes. We're going to be having a Q&A after the presentation, so any questions or anything you guys have, please enter them into the chat, and we'll try to answer as many as we can at the end. We'll also be entering in some downloadable content into the chat group as well on some of the topics we're discussing and some other just general knowledge about Promess and some of our systems that we offer. We also, if you're looking for more additional content on webinars and educational series and videos we've already done, if you go to our website at promessinc.com under the resources page, we have a list of videos and things that we've uploaded that you can request to see, and we can send you a video for that link. So let's get started here. So Glenn, what are some challenges that you've seen in assembly processes out in the field at our customers?
So to preface all this, there's generally two issues I generally see. So I'm going to start with the first and probably the most variable of the two. That is issues with your parts or inconsistencies with your parts. And these things can range from things as simple as the nature of the part. Maybe you have a large part that's got a lot of deflection to it. One transmission case to the next transmission case doesn't quite deflect the same way down to a very, it might be within a millimeter, but it's, when we're talking about microns, it's not consistent. You might have changes from batch to batch. You might have, this week we ran on this batch of bearings, and next week we're going to have a different batch of bearings. And even though they might be in the same tolerances, that day they were running a little bit, differently. So the bearings are a little bit different. And that leads into the other part of changes in machining, where you have potential issues where maybe as drastic as a machining issue, a machining problem, where the part is so inconsistent or so different than what you're expecting, from part to part, of course, that you might run into issues. One of the best example of this I ran into a few years back was we were actually pressing a bearing onto a shaft, and we found that the seat force was sitting, or the seat position was all over the map. There's a pretty wide range of where it would sit. But eventually we could track down that there was actually a lathe that the bit was actually worn down on, and it wasn't machining all the way down, or was machining inconsistently. So the bearing was kind of just all over the map. So you run into issues with parts. The second broad category that I generally see is issues with what I call the station. So these are issues not with the part coming into the station, but the actual machine itself. Now, this can be things like, here we have a press that's on a C-frame. It could be just a deflection of the C-frame across the yaw. It might be flex or stack up shifting when the part's actually in the station. So generally, to go a little bit more into detail, I break these out into two kind of categories. There's tooling and fixturing issues where there's kind of stack up, but then there's also temperature and environmental effects. So things like, on a hot, humid day, all of this is going to expand, and on a colder day, this is all going to retract. So things start to get inconsistent, and from when we're looking at microns and thousandths of an inch, where the press goes to in space is not always the same day to day. Now, part of all these issues can kind of be fixed kind of be alleviated with using a probe. So Scott, what is a probe, and how do you see a probe fixing some of these issues?
So a probe is a high accuracy external linear measuring device. So there are various different types of probes: analog probes, digital probes, lasers, and they come in all different shapes and sizes. So typically at Promess, we normally use digital probes. And like the one we have here, this is a 25 millimeter digital probe attached onto this demo press here. So meaning it has roughly 1 inch of stroke, or 25 millimeters is equivalent to 1 inch. So it has 1 inch of travel that this probe can measure and monitor. And we also offer, there's, just as an example, smaller probes like this would be a 12 millimeter probe, and we call it a pencil style probe just because of its different shape. So it's, in general, when you want to pick a probe or trying to use a probe in your application, it really just depends on what you need to measure, where you're going to measure, if there's any physical requirements as far as if you're using very small parts you're assembling, or if it's a long stroke length you want to measure, maybe you need a probe with a couple hundred millimeter stroke. So it can vary from application to application, and it's really, there's no one specific probe that's going to solve everyone's problems. It's, there's a wide range that are generally, you'll be able to find something to help improve your process. So when using or incorporating a probe into a press system, just kind of take a step back. So all of our presses have integrated force transducer here built into the system. So we get force feedback from this load cell up here, and we also get positional feedback from the motor that's here mounted in the back. And any other devices or probes that would be added to the station would just be another control input that would be fed back to our controller. So when using a probe in a station like this, typically you might have, maybe the press ram would use the position input from the motor to wrap it in real close to the part, maybe just above the spring. And then in our program, we would switch over and start monitoring the control input from this probe. So as the press extends down and contacts the probe, we're going to press or stop to a position based off of this probe. So typically when using a probe in an application, it can be mounted in many different spots. It's really, there's a couple of main things you want to consider are, it's always going to be measuring on a controlled surface. So, not like a painted surface or something that it's going to vary from part to part, because that's not going to help you get repeatable results. So in this case, we're using what we would call a flag. So if the tooling's on the press ram, we would have a flag that sticks out. So this is not ever going to be under load, and it's always going to be solid. So the probe's going to contact it in the same spot every time. So as it comes down, the flag will contact the probe, which is mounted into the base fixturing, and that's going to determine where the press presses the part to. And also, inverted from that, sometimes the probe actually might be mounted onto the end of the press ram. Maybe on the flag, the probe would be mounted off to the side somewhere, and then we would actually be touching off on the part when we're going and pressing down to the part. So if the probe's contacting some sort of controlled surface that should always be consistent from part to part, we can incorporate it either into the tooling or into the base fixturing or wherever makes the most sense for the application to get repeatable and accurate results. So as Glenn alluded to earlier, the benefits of having the probe mounted down here in the fixturing is you eliminate all out of the inconsistencies. So from part to part, if the part heights vary that you're getting in, or from batch to batch, they change. Or even, we have deflection in the C-frame or whatever the press is mounted to in the press, in your tooling, you're eliminating all of that by measuring directly on the part itself. So we don't care how much force it takes with deflection and how much movement we see elsewhere. We're getting consistent results because we're measuring directly at the part. And one of the other main benefits of using a probe is just its accuracy. So typically probes are accurate to within 1 micron or even a half a micron. And so Glenn, if you like, what exactly is a micron?
Yeah, so we've been throwing around a micron a little bit around in this talk here. And we kind of throw around just micron just in general here because it's kind of a token phrase for us, because a micron, the actual definition of it is it's 1,000th of a millimeter. So there's 1,000 microns in a millimeter. But it's also generally the smallest unit of accuracy that you see in a production environment. Now, that doesn't necessarily mean that people are, pressing a part down to 1 micron or within 1 micron, but generally you see, it's not uncommon for us to see a spec or something that comes in and says, this has to be pressed within 10 or 15 microns. Now, for those of us, I tend to see, in a production environment, a lot of times we're dealing with European standards, so we're in millimeters. But for us on this side of the Atlantic, it's comparable to 1,000. The 1,000th or a thou is 1,000th of an inch. and that comes out to be about 25 microns and some change. So for whenever I say a micron, if you don't normally deal with that, you can always think of it as 25 microns is a thou. So, and just to get a conceptualization of how small that is, an unaided eye can see, the average person with an unaided eye can see about 40 microns, somewhere between 30 and 40 microns. Now, to give you even more of a conceptualization, that's about half the diameter of the average human hair. Fun fact, because it's spring and I have allergy problems, it's about the size of a pollen particle. So when you walk outside and you see some pollen around, that piece of pollen is about 30 microns. So when we're talking about manufacturing down and monitoring down to microns, it's small and it's very precise.
Very challenging.
So when we talk about these kind of things and kind of just gauging in general, there's a lot, if you even just this simple stand, there's a lot going on in a lot of places where deflection, where microns can come out of nowhere, if you will. By taking that probe and putting it and using its high accuracy away from all of this directly at a machine surface, you kind of rule out everything. You rule out all the wayward microns that come out of nowhere. So I know I have a lot of applications that I have running in my mind. Do you have any applications that you can think of where we have used the probe and it's made the part better?
Yeah. So one application in particular is control arms, pressing bushings into control arms. So this is something that Promess does quite a bit. Excuse my bad drawing here. Not the best artist, but so if you have it, so when you have a control arm, we're going to be pressing in two bushings. Typically the bushings get pressed from the left and right side like this. So you would typically have two presses that would come in from each side to press in the bushing. So the main thing when assembling the control arm is the critical dimension. It would be the inner dimension of where those bushings end up. So this inner surface in relation to the center point of the bushing is very critical. So when the control arm is going to get assembled into the component or vehicle, it needs to fit in securely. So if these bushings were pressed in too far and the bushings were too close together, it's not going to fit in the vehicle. If they were pressed out too far, it's going to be sloppy and there's going to be way too loose and it's going to cause issues. So the challenges with pushing is with the press going in from this side, we could press the bushing into the same exact position, on the surface we're touching every time. But with bushings, being made of rubber, and the important control dimension is the inner dimension, that's exactly where you want to be measuring. So in order to get repeat and accurate assemblies, we have two digital probes that we would add in on the inner part of the system right here that would directly be measuring the end of that bushing. So we press in one bushing, and typically even when you're pressing that one bushing, you're going to see it may take a couple thousand or several thousand pounds to insert that in. So you're going to get deflection on the part, deflection on the frame, and everything. So not only are we going to measure where we press to, but one of the key important things is we actually back the press off. So we apply the load, press the bushing into some specified point based off the probe. We stop, remove the force, and then we look and see what that probe value is. And if it's still not at the target, or we might need to make an additional correction, we do a calculation in our software to determine how much farther the press should go back and press the bushing in again. So typically this could be something that maybe we would do in 2 tries, or sometimes maybe it takes 3 or 4 tries to accurately seat that bushing to the correct spot. And then we would switch over and do the same process on the other side. So you're monitoring, so not only are we assembling it, we're essentially kind of testing it in the same station, because we're verifying that inner dimension, which is the critical part of this application, is going to be exactly perfect for every single part. So it doesn't matter if the bushing tolerances vary. So we have inconsistencies in parts. Sometimes bushings may be 3 or 4 millimeters different from part to part. And just with the rubber and everything material they're made of, you get a lot of spring back, and it changes and moves after it's been pressed in. So you're getting more consistent assembly. And one of the other key things to do too, also when using probes like this to not only assemble and test your part in the same station, is it should be able to correlate to an offline gauge. So when this part's assembled, if it was taken and put in an offline gauge at a customer's, I'd imagine that they should measure the part in the exact same way that the probes are contacting it during the assembly. So that's how you can ensure you're not only assembling and testing and making repeatable or clonable parts, if you will, every single cycle. So that is one that we've definitely done quite a bit of. Almost all vehicles have these in them, so we've been doing this process for many years now.
Yeah, the big thing is even, and to kind of go back to some of my part inconsistency talk, it could be something as innocent as, the control arm, the kind of alloy or the consistency of the alloy that when it's made, that's nothing that anybody really controls, but it can have an effect on how much that control arm is deflecting as you're pressing the bushing in. So sometimes it's got nothing to do with, it's not even a manufacturing error. It's just, just the nature of the part. It just is what it is.
Yep. Yeah, and also too, so if you do you want to look up some more information on control arms, we actually did another whole webinar series. I think will be posted in the chat that goes into a lot more detail about that application and just other things in general about assembling and testing parts in a station. So
it's definitely a popular application around here.
Yeah.
One application that I was thinking of, and you're going to have to bear with me because there's a little bit to this. So it's actually a magnetic or a magnetized pulley put onto a motor. Specifically, we're pressing onto the shaft. So there's two parts to this, or two parts to this part. There's the top piece of the motor, which has a chip that stands off, and then the motor itself with the shaft that we're pressing the pulley onto. So in this application, there's actually two probes. Now, one of them is a laser probe. And this laser probe, when the part comes into the station, it's measuring off that chip. And specifically, there's a few, mastering devices that are used before the shift runs to determine, essentially what we're trying to determine is how far is that chip standing off the top of the top plate. So when it comes into the station at the start of the press cycle, we're using that probe measurement to determine how far we're going to press the pulley onto the probe or onto the shaft. And this is so when they actually go to mate these two pieces together, they mate perfectly.
And there's that gap between the pulley and the chip height is very critical, that it needs to be at a certain distance.
So then the second probe is actually attached to the press ramp. And that press ramp and that probe touches off on a machine surface on the motor. Again, the machine surface part of this is critical because that gives us a very specific datum that we can touch off of and tell where the pulley's at in space. Again, bypassing all of the potential deflections. And there's an extra wrinkle to this. It's a magnetized pulley, so it does slip and slide in unexpected ways. But at that point, the way it slips and slides, it doesn't, we don't really care. We just go to the probe value. So once the target on that probe value is determined by that height of the chip. So like Laske said, when it mates together, there is a very precise gap between the pulley and the chip. That's just kind of one. I like that application because it encapsulates the two things that you would use a probe for. One, determining where to press or how much you're going to press, and determining where the part's actually in space, which is kind of the critical part of these probes. But do you have any other applications you can think of?
No, I mean, that was a good example because it's not only just using one probe and touching off in one spot. Some applications require multiple probes, measuring different components, or just measuring multiple surface areas of a part and then taking an average. Sometimes if we measure 3 or 4 different controlled surfaces, just to ensure the flatness or squareness of a part. One application that comes to mind, it's more just kind of a general one that we've done quite a bit, is any sort of bending or straightening application. So there's a medical device that is used on the end of a surgical robot arm. And we were bending that blade to put a certain radius or bend to that to allow it to make a good cut. So it was really critical that it had a certain bend or radius to it. So we're using a probe similar to this, where the part would come in and contact off in the probe. And then as we're pressing and bending that part, we bend it to a certain fixed value. Typically, when you're doing bending and straightening, you don't want to go right to the perfect spot at the right time. You just want to be close, because if you overbend it, there's no way to come back. So we bend it to a certain location. Again, then we would back the press off, but the probe would still be contacting the part. So whatever spring back or wherever that part settled, we then in our software determine where it's at, where we need to go, and do the calculation to determine where we should press to next. So some of these applications, again, we might press 2 times on the part and get it to that perfect spot. Other times we might hit it 3 or 4 times, but that's all how you would program or set it up in our software to how many retries you want.
Yeah, and the amount of, I mean, we've done a lot of bending applications in the past, and it's the bending is another good example of this, because bending, you have to determine how many probes you want to use, because depending on what kind of radius, what kind of angle, what kind of degrees you need to press it to, but also where and how. There are actual straightening, the opposite of bending is straightening. You got to use, we have some straightening applications where we have to use multiple probes to determine how straight it is.
Mm-hmm. And maybe where in the part it needs to be. So if the part is not straight in the middle or end, the part could be on a slide. I could rotate and move on to the press to where we press on it.
And again, even though we have high precision from the motor, we don't even have to consider the station in those kind of applications, because you're literally bending the part. The spring back's potentially not consistent there anyways. You need something that's going to touch the part specifically and say, okay, this is where it's at. This is where it's at in space. Is everything flat? Is it where we need it to be? But all this.
Yeah, just to kind of reiterate again, it's one of the main thing whenever you're using a probe, if typically any part that gets assembled, normally there's some sort of offline gauge at some point that is checked to make sure it's assembled properly. So depending in wherever you're measuring with your offline gauge, that should it should be incorporated into the assembly process. So you really can assure that you're not only just assembling the part, you're testing it accurately, and it's being made identically in the correct way.
Yeah, because all this talk actually reminded me, you had mentioned flatness and squareness earlier. There's actually an application that we do where we're pressing a seal on the end of a crankshaft. Now the thing with the seals is it's very finicky, that you got to make sure that it's perfectly going in straight and so on. You can go to a certain force, you can go to a certain position from the press ram, and that sometimes there's a strong correlation, but not a perfect correlation when you want to make perfect parts. So in that specific application, we actually have 4 probes. All right, there's actually another one. There's a similar one that we have 8 probes on, but for this one specifically that I'm thinking of, we have 4. And the 4 probes are actually mounted to the seal. So when the seal's coming, so when we press in the seal, we're actually using what we call a math-lab variable to calculate in real time as we're pressing in the flatness and the squareness of the seal as it's going in. So you get kind of a real time, okay, is it coming out of squareness? Is it not flat? Just to keep this critical, and really we mimicked it off of, specifically the placement of the probes, we mimicked it off of how they used to gauge their old systems. So before they would just slam it on. They would just slam the seal on, 60% of the time it was perfect. The very next station they'd come in and they would basically just attach this tool that would measure how flat and how square it was. Well, this is essentially taking that tool and putting it on the end of our press ram, and we essentially do it all in one go.
Assembling and testing all in one.
Yeah. And the big part there is it's multiple probes. So sometimes it's not as easy as pressing on a spring and having a probe. Really where the money's made in the probes is you got to figure out where to put them and how you're going to do it. Do you have any other applications you can think of?
Not really. I mean, just any kind of bending or straightening, but it really just comes down to lots of times if there's certain applications where we're trying to hit a window, maybe like a 7 to 10 micron window for lash on a pinion shaft. It's one we've done before. It's a little more complex, but so it really, the main thing is not only you're making a part, but you're able to measure it too with the probe. That's one of the biggest benefits. So you're making and measuring a part in the same station. So like Glenn just alluded to, instead of assembling a part and then the next station has to be the gauge and test it, and then it's bad, now it's got to resend it to get reworked on, we got to press it in again, and that takes time, and time is money in assembly processes. So you're accurately assembling the part. You're ensuring that every part, no matter how inconsistent the parts may be or whatever deflections and other tool machine issues you could have, that's all being eliminated by adding just a digital probe. It's for fairly low cost solution for what you're able to accomplish with it sometimes.
Relative to the money lost and otherwise, it makes up for it.
It's very beneficial. So I think we're ready for some questions now. First one, would you consider a digital probe a linear encoder?
So there's a little bit of a technical semantics thing. So our digital probe, so somewhat by definition, a digital probe is a linear encoder. So there's a few, essentially the probes that we use and generally that are used in the industry, there's kind of two types. There's an analog probe, which is an LVDT, typically an LVDT, or a laser and some kind of linear voltage measurement, or potentially a current measurement. The other is digital, which would be, we use quadrature encoders, but there's other like TTL and things like that. So hopefully I answered that question for you, but it's a little bit of a semantics thing. But really we've used, if you haven't picked up from our application experience, we've used essentially lasers, LVDTs, digital probes.
Air probes where, whereas an air cylinder to fire and retract, it's
really anything that gives a signal in either an analog or a quadrature encoder to measure out and correlate to a distance.
Is there a lag time between the measurement from a probe and the system reacting? No, not really. It's the same thing. So you think, we have position feedback is just another control input going to the drive. The force feedback is another control input. And then same thing with the positional feedback from this probe. It's just another input to the drive. So the press is going to react very, very fastly to the position change of this encoder. And then that's also determined too, what you set speeds, accelerations. There's a lot of other factors and variables that go into how accurately and how you want to stop. So depending on the application or what it requires and accuracies, that's all something that's kind of determined application based.
The big thing to stress what you said first. A lot of times in our nomenclature, we have a move to signal. Now in the old days, it used to be a move to force because that's all you used to use. Was you only press to the force. But in our system, we essentially treat this as another signal, so we can move to the signal as accurately as we move to anything else.
So that's what the step is actually called in the probe. It's called the move to signal step. So whether it's the force feedback from the press or the position feedback from the probe, you set the step up using whatever input you want.
We've used flow meters, we've used pressure sensors,
current, whatever. It's just about anything really. Is it better to install the probe on the press or on the station itself?
So depends on your part. And I know that's kind of a little bit of a cop-out here, but the biggest thing is, and we've stressed this before, it's got to be a machined or consistent surface. Now, on a setup like this, it's pretty easy. Everything's in air. We got a lot of room to work with. Now, if let's say you were trying to press a part into or use a probe to press a part into something like a transmission case, something that's very non-uniform, it's big, it's into the part or something like that, you might have to put it on the end of the press ram. Or if it's something where specifically, maybe we're trying to measure a dowel height, or a dowel height's a good example of this. Maybe we want to press a dowel to a certain dimension here. We can press this probe or have this probe off the center of that dowel, away, part of the fixture or something. So we know that dowel is going in as deep as it
or like
should.
The bending and straightening applications. Those you would definitely want the probe to be mounted onto the base and actually touching the part, because you want to run on the press ram because we press on the part, but then you have to remove the load and still be able to accurately measure. So really, it's just whatever makes the most sense for that application.
That's definitely the Lego piece of this whole equation, is where it really depends on. The biggest thing is it's got to be on a machine controlled surface.
How accurate is the press without using a probe or an LVDT? So it's a really good question, and there's not really just a one answer for anything. There's a lot of variables and factors to consider. So a lot of the things that we alluded to before. So whenever the press, the temperature of the room that the press is in and operating in, what kind of tooling and everything, equipment do you have mounted to the end of the press ram? So you'll have deflection and everything. So there's a lot of factors. So as a general rule of thumb, we basically kind of say the press as just off the position from the motor alone is accurate to within plus or minus 25 microns. Now, typically, it's we're more repeatable than that. So if you just want the press to go down to one position and back up and back down, that we can accurately hit that position every time. But just general accuracy is kind of 25 microns, I'd say.
Yeah, and the big thing, just to kind of draw it out a little bit more, part of it is essentially the press as it heats up, as it cools down, different environmental
thermal
factors,
expansion.
it starts to expand, and that's how we get high repeatability, but not necessarily we have 25 microns of accuracy or depending on environmental factors. So it will, like Laske said, it will hit the same spot in space every time, but whether or not that's actually 25 microns or 50 that's a different question.
What is an LVDT versus a digital probe?
So kind of going back to one of the earlier questions, an LVDT is a linear voltage distance transducer. So essentially that is an analog signal. So as the probe is depressed, as I would depress this, even though this is a digital probe, as I would depress this, there would actually be a difference in how much voltage is going back to the controller. Digital encoder, there's actually separate poles that as this gets depressed, it sends different pulses out to basically tell us how the probe is incrementing. So really, in function, if you were going to talk to your manager or something like that, they more or less do the same thing. An LVDT in certain circumstances might be a little bit less accurate, but it is generally cheaper because it's a little bit less robust. Mm-hmm. But for the most part, they're kind of the same thing. Yeah. And really, when I've run into it, I almost, my mind immediately goes LVDT, digital probe. It's all just a probe. Yep. We just treat it the same way.
All right. So it looks like that's all the questions. Thank you guys for joining us today. Hopefully you learned some things. And if you do have any additional questions or anything, you can always email us at promessinc.com or Promess support at promessinc.com. Yeah, anything else you want to add, Glenn?
Or you can give us a call at 810-229-9334.
All right. Thank you.
Yeah, thank you.